Professor Zhong Lin Wang is a Zen professor at Georgia Tech and director of the Beijing Institute of Nano Energy and Nanosystem. Dr. Wang pioneered the nanogenerators from fundamental science to technological application. He is ranked the 15th among 100,000 scientists across all fields worldwide. His Google Scholar citation is over 250,000 with an H index of over 245, including Albert Einstein World Award of Science and any award in energy frontiers. He received many prestigious awards. Without further ado, please join me in welcoming the Professor Wang.
Hello, Professor Kim. Can you see me? Or hear me?
Yes, I can see you.
Yeah. First, I'd like to thank you, the organizers, give me this opportunity. And I visited KAIST last year, and we planned a lot of things for the discussions, collaboration with KAIST this year. But due to the pandemic, we could not do anything right now. But we can do online information exchange and conference. So thank you for organizing this meeting, and also be happy to share what we are doing in the last few years. So my talk's on the science of contact-electrification and the technology of, let me see, okay, let me get a laser pointer, okay, and the technology of triboelectric nanogenerator. So my talk is basically focused on the energy. As you see, the energy is broad, very broad, from classical coal technology, oil, to solar cell, battery, all these things. So as we move to the new era of technology, we are looking for small things, especially once nanotechno upcoming, people looking for driving small device for Internet of Things. So this drives us to new energy for the new thing and energy for the future. So there are two ways to deliver energy. One is the traditional power plant. The other one is the storage units. Through both ways, you can meet large percentage of the need for power, okay? So today's society is advancing. We never thought about this before. Today we have all the different devices, mobile electronics, tiny device for medical applications, and big data. We want to measure a lot of things, know the position, the speed, acceleration, and the three-dimensional coordinates, everything we want to know. But all this one rely on the sensors. So all sensors has to be powered. So therefore, today's power have two parts. One part is the traditional power. The other one is the power for Internet of Things and the sensor networks. So as you look at this furthermore, the way of our look at the power has been changed. A lot of way we think power is from the power plant to factories to houses. Now this is the ordered, highly concentrated energy delivered by cables. But now look at what we are facing now is called the distributed energy for driving those small electronics. This is what we are working on right now. So two parts of energy for the fixed sites, energy for mobile on specific sites, and a large number but small power of each. This is what the way we look at the future here. So therefore, when you look at power, not only just count how many megawatt, gigawatt you can generate, is how can you effectively deliver to those devices which are needed, so you can maintain free and can be sustainable development. So when you do this one, you have look at how to solve this problem. So 15 years ago, we started working on this problem. So we call it self-powered system. So we have a system not only can sense any sensors, any information you want, but they have to deliver the information to the outside world. So if we can harvest energy from the working environment, we can drive those devices to send a signal wirelessly. So therefore, this is called a self-powered system for that. So when did we start this work? This is a story. This is a big back to 2005 and 2006. We work on the growth of nanowires, and we use an AFM tip to measure the piezoelectric response and we found there was a voltage and a current output. So that time is just nanowires. We generate nano power. We call nanogenerators. So as a result, this field advances a lot, especially in a few fields. For example, nanogenerators, cell power nano systems, and piezoelectronics for that. So with this field advances, there's different ways to do things. I'd like to give you the most update, theoretical, experimental, and technology applications here. Okay, so when we do this one back to then, this was the let me see. This was the wait a second. Okay, laser. Okay, this experiment we showed that before. We utilize for heartbeat driving and hamster driving electric power. Okay, so those ones, if we did this about 10 years ago, was used piezoelectric effect. But as we move along this time, okay, and we move along, we invented the triboelectric nanogenerator TENG in 2011, and we have a lot of people in Korea and worldwide work on this technology now. So what's the difference? Let me show you the difference. You can see this is the way it drives. You can see that, oh, sorry. Okay, this is the traditional way for power generation. This is the way we do. And this runs as fast frequency, and this is as a slow frequency. So at the lower frequency range, you can see that the power delivered by TENG is a lot higher than electromagnetic generator at a low frequency. So as you see from this video. So as you see for the energy harvesting from our living environment, we most face low frequency. So this demand talks about how can use TENG to harvest energy from our living environment so that can be effectively utilized for power small electronics. Okay, so in the last few years, that the TENG has been explored for micro nano powers, even cell power system and blue energy have many interesting applications here. So let me just go to the fundamentals. What is the science about this technology? And what are the theory for the current we can quantitatively calculate? Let me show you this one. So my outline talks basically a few parts. Let's talk about the physics first, then we'll talk about the figure merits and the final application. When you talk about the application part, okay? So what is contact-electrification? Contact-electrification is a well-known phenomenon. People normally call triboelectrification. It's known for solid and liquid, okay? But the question was that why one things rub against the other, you're gonna have electrostatic charge on surfaces, and the plastic rod has negative charge, the animal fur has the positive charge. This is called electrostatic charge. So let's understand the physics about that. So this is a very old phenomenon, but not well understood, okay? So when you look at this one, okay, it's an unsolved problem. Many debates, is electron transfer, ion transfer, even materials transfer, and it can be happen for solid and solid, liquid and solid, liquid and liquid, gas and liquid, anything you can think about that. So it's a broad effect, happens for any phase of materials, any materials you're talking about that, okay? Okay, so this one, let's talk about the fundamentals here. The fundamental is that if you look at the textbook in the middle school, the students here, they talk about the electrostatic charge. Electrostatic charge, suppose on the surfaces cannot flow, but then the class talk about the current. So from the flow of electrostatic charge to current, there's a gap. Did not answer the question. So let me show you one by one. First one, how the electrostatic charge being created. The second one, how do they flow? Okay. So the first question is physics of contact-electrification or physics of triboelectrification. So the basic principle is this: two medium contacts and get a small power output. Then small power output here. You can see very simple thing. Many groups can do it. And I have this one in my hand. You can see a copy of this one. So if you press this one, it's live flashes. It's live flashes here. Do you see light? Let me see. Yeah, you see live flash here. Okay, so with this is the way for the power generation. Let me show you the basic physics behind here. The first one, why the two material contact have electrostatic charge created. So we did this experiment a few years ago. I said two medium contact. We started temperature dependent. We put the TENG inside a furnace. We found when the temperature raised by 563 Kelvin, there's no output. So output drop to zero. So therefore, there's a up limit temperature up to which the TENG works well. So that means there's a model for the charge to decay as a function of time. If you fix it at the 443 Kelvin, that's this curve, the charge on the surface of the medium drops slowly. If you hit the higher temperature, it drops immediately. Okay, so these things draw our attention to the charge releasing mechanism. Basically, if you have a metal, okay, with the vacuum, you have a barrier here. If you apply to certain temperature, the electron can be emitted, called thermionic emission. This is a well-known phenomenon in the physics, thermionic emission. So as time goes by, electron through tunneling effect gradually disappears. Okay, so we start this use AFM. This AFM can control the tip temperature and the substrate temperature. If you fix the sample temperature 313 Kelvin and raise the tip temperature from the same temperature up and up, you can see with the increase the temperature difference between both, the transfer charge increases. This is because at a certain temperature, the distribution of electrons around the Fermi level is called the Fermi-Dirac function. This is called the Fermi-Dirac function. This function is that have a little tail. So the higher the temperature, the longer the tail. So when you contact with the dielectric, unoccupied surface states get electron transfer. So more electron transfer to dielectric. If you raise temperature, the tail get longer, more electron transfer. That means the data we show here. So this is a simple case, metal with dielectric, because metal have free electron transfer. However, when you have two dielectric, they can also have charge transfer. And these studies, we try to manipulate this one, say, okay, we have a tip, we have a dielectric, we can make the electron go from the metal to the dielectric, from the dielectric to the metal. Let's try how to do this. So you raise the tip bias, you apply a bias to the tip, you can deliver charge to one side or reverse it. So this reverse by the bias is because we shift the Fermi level of the metal up and down in reference to the unoccupied surface states of the dielectric. So if you go to negative bias, raise the Fermi level, more electron transfer to here. That's what this case. If you go to positive bias, lower the Fermi level, so electron can transfer from the silicon dioxide to metal. You can reverse these two. We can reverse. That's what you see experiment here. The key question we try to answer here, the charge transfer here is due to electron. If you have an ion transfer, you can't have the reversal sign. So this electron transfer give you one. Because at the very beginning I said it had been debating electron transfer, ion transfer, even material species transfer. Our conclusion is mostly electron transfer. Okay. So now the next question is that for the sample, how close the tip has to get to the sample before the electron transfer occurs. So we use a tip study with the dielectric surfaces. And how do we know how close the tip goes to the surface? We measure the tip interaction with the sample through the phase of the tip oscillation. So we found in a repulsive region, there's charge transfer. In the attractive region, there's no charge transfer. You can see this is the voltage. Kelvin probe measured the voltage on the surface, and this is the phase of the tip oscillation here. You can see in the attractive region, in the repulsive region. We only in the repulsive region have charge transfer. So what's going on here? So we need to propose a generic model for the case, because contact-electrification occurs for any materials. can be crystalline, amorphous, can be any material you talk about. Fur, fiber, hair, jackets, soil, everything. So if you have two atoms here, interatomic equilibrium bonding length is A. So this is the interaction potential here. If you squeeze one against the other one, you maximize the overlap electron cloud. In such a case, repulses each other. They repel each other. We experiment find this is the only region the electron transfer occurs. So in order to have electron transfer, you must have the large electron cloud overlap. This is the case for that what you can have the attractive region. In attractive region, there's no charge transfer. So therefore, in the experiment, why do you have rubbing one against the other one? Is to make 2 points so close, have a larger overlap electron cloud, so electron transfer occurs. Okay, so this is the simple expression. But if you make this looks more realistic, is look at one atom like this, separate too far, the barrier is too high. However, now if you have push one against the other one, so barrier is lowered. Barrier lowered, the electron transfer occurs. So how does this happen? Let me use the animation to show you. This is the one atom, the other one separate too far. So if you push one against the other one and have a large overlap electron cloud, so electron transfer occurs. They cannot go back unless you apply a temperature. So therefore, this is a simple, clear model for explaining contact-electrification for general materials for here. And you can use, of course, you can modify, use band structure, but more or less case is relying on this electron transfer between the orbitals between one atom and the other one. So contact-electrification is complicated. It's also happen for liquid. You see, the water flow from the liquid with the glass bubbles here. Here you can attraction here, and why the liquid have charge? So liquid have some kind of charge with the solid, then liquid is charged. So now let's look at the case. This goes back to most fundamental question for electric double layer. If you have a solid, you have a liquid and a surface of contact, and they assume you have a layer of ions, and then the ions in the liquid freely distribute from a electric double layer. You can have the stern layer, you have the bare length to describe potential difference across here. And this phenomenon is fundamental chemistry to electrochemistry and many field, because it is respond to many things in our daily life, like the suspension of milk, blood, paint, everything with this kind of chemical engineering. So the question is that, are these ions or any other charges? So we try to challenge this model in this way. Let me show you what we did. Okay, so what we did was we have silicon surfaces. We put a droplet of water on this one. Let a droplet of water evaporate. Before we put the water on, we make sure the surface have no charge. Use a variety of techniques such as like laser radiation, UV radiation, and heating, etc. And then when the water drop on that, and then we wait the water to be vaporized, we measured, we find there's charge on the surfaces. So there's charge transfer between water and the solid. Then we heat up the substrate. After water vaporizes, so there's a dry surface. We heat up, we find the charge decays. Then you see the charge decays didn't drop to zero, from minus 800 to minus 200 microcoulomb per meter square. This is the residual ions remain on the surface. This electron get rid of because the electron is more sensitive to thermionic emission, but the ions are not because the temperature is not that high enough. Then, so we initiate the virgin surface, apply water, this is the surface charge, dry the water and irradiate it with some apply heat. This is the ion residue on the surface. Second drop, the charge raises to here, dry and get rid of the electrons, ion on the surface. Third drop, fourth drop. So after a number of drops of liquid on surfaces, if you repeat this heating process, get rid of the electron, you have a steady charge on surfaces. So therefore, eventually, you have an ion on the surface, but at the very beginning, you have both electron and ion transfer. This is because you cycle the heat the sample. But if you don't heat, you have this one, this could be remain there for a very long time. So therefore, we have both electron and ion transfer. Okay, so this is what we try to say. Basically, the number of charge density on the surface is fixed, but when the first water drop comes on, both electron ion goes on. You heat it, electron emitted, ion remains. Second drop, more ion on the surfaces, get rid of electron. Third drop, eventually reach a saturation here. So that's what we found here. And this model we have studied a lot in the last 2 or 3 years. And I think it fundamentally could be fundamentally important for chemistry and many interface sciences here. Okay, so then we use this one to change the concentration of molecules. We find, regardless of concentration gone on, eventually the surface after some time decay. This is the residual ion on the surface. You repeat this experiment, you can get this cycle, the oscillation here. And this you can change pH, pH 11, pH 3, different sign of ion on the surfaces, respectively hydroxide group, protein group, okay, proton group here. Okay, so this is, you can change the pH, the concentration, but to verify this, the model. This is the liquid and the silicon surfaces here. So this goes back to the model we proposed some time ago. Okay, so if you have a virgin surface, when the liquid first on the surfaces, then you can have both electron transfer. The water can become a water molecule. Okay, water molecule can become water ion. This water ion that recently found do exist, except the lifetime is shorter. So you can have the electron transfer, ion transfer. Then if you heat up, then some of the electron disappears and some ion can be a continuous soap. So we found the average distance between electron is 16 nanometers. The average distance between the absorbed ions is 30 nanometers for that. So you can have physical absorption or chemical absorption on the surfaces, different sign of ions with electrons on the surfaces, just depend on the condition you're talking about that. So this is, so on average, it's 1 charge per 10,000 atoms on the surfaces here. Okay, so I think this can have some revisit some of the fundamental effect, because electron double layer is important for physics, chemistry, and many fields here. Okay, and the second case can be liquid and liquid. Let me just skip this case because I think the time goes very quickly here. Let me show you. We in a liquid like oil and oil and liquid, oil and water. We also can find there's interface charge here. The TENG can be a probe on the surfaces here. So this is the charge, the interface of between oil and liquid can be negative and positive. So this can be a probe to probe the liquid interfaces here. So this is what just the preliminary result we got and for this study. So contact-electrification is a type of physics effect, but traditionally people make it complicated. Always with triboelectric. You have triboelectric. Why do triboelectric? The rubber one against the other one, charge transfer occurs. But now we think you don't have to do triboelectric. You just two things contact. Two things contact have charge transfer. So contact-electrification is a quantum mechanical electron transfer process that occurs for any materials in any states, solid, liquid, gas, in any application environment and a wide range of temperature range up to 400 degrees C. Such effect is universal, is fundamentally unique in nature. So used to be we make things complicated. Tribology, convolute with contact-electrification, we talk about triboelectricity. So therefore, the future scientific you should call contact-electrification, in generic call triboelectrification. Both have difference. So this is the first question, how the charge generate. The second question, how the electrostatic charge flow. This goes to the basic principle of TENG. The traditional way we know is the current is called conduction current. Magnetic field use the Lorentz force drive electron to flow, you form a power generator. So this is well known. But now we talk about a so-called displacement current. Displacement current was first proposed by Maxwell when he unified electric magnetic field. So now this one did not count for the effect we're talking about. So if you talk about displacement current, it says displacement current is in the is not electric current of moving charge, but a time variation electric field plus a medium polarization term. This is a medium polarization term. In our case here, you have a piezoelectric effect, triboelectric effect, you have a surface charge. This, if you change the configuration of the medium, you can produce another term in the displacement current, which term was not included in this more conventional use equation. So let's introduce this into the equation here. So you can use this one for piezoelectric case. You can work on the charge. This is the medium polarization and this displacement vector. You substitute this medium polarization into here, you get a permittivity plus E, multiply E. So displacement current is this. If there's no variation in electric field, there's no displacement current. That's called electromagnetic wave. But now we have a residual charge on surfaces. You need to add a term. This term is the current you observe here. Okay, you see this current is observed here? Okay, this term is the current you observe here. Is due to the medium shape change introduced to the displacement current, which is due to surface electrostatic charge here. So we work on this one a lot. Let's see how do we formally include this in the field. If you quantify this in the previous slides here, let's see in this experiment. What you see is basically two medium contact electrification. But this term has to be included in a definition of displacement vector. This is displacement vector. So medium polarization is epsilon minus epsilon 0. If you include the surface charge due to the contact electrification, we should modify this. But how do we modify that? So we need to add additional term here, which goes to the next slides. If you do not include term, this is the displacement field. We conventionally utilize this, and this is why you cannot derive the output of TENG. So you add an additional term. If you add additional term, you need to substitute this one into the original Maxwell equations. You substitute in, you get a new equations here. Is this the space charge, this displacement current here? If you redefine the charge density, current density, you can recover the shape of the Maxwell equation. But the difference here, you include both into the displacement current. This is what we observed experimentally. So this term is responsible to the electromagnetic wave. This term is responsible to the output power of TENG. Both have a large difference in frequency, so they cannot couple with one the other one in our case. But in future, if you can run this at a high frequency, you could have a coupling, but we can treat them independently. So this one is what we showed here. So basically, this term is responsible to the electromagnetic field. The second term is responsible to the power generation. We talk about that. You can do a lot of calculation here, and I don't need to repeat how to do numerical calculation to calculate output power, output current, quantitative for any configuration. You're talking about that, and we have a recent review in applied physics. It's a very nice comprehensive review of the theory in this regard. Okay, so let's make it clear. This is we have two current, conduction current and the displacement current. Conduction current is the way for electromagnetic generator used to be. Displacement current used to be called for electromagnetic wave. But now if you have this term is for piezoelectric nanogenerator, triboelectric nanogenerator, and other nanogenerator as well. So therefore, when we first named the nanogenerator, we talk about use nanomaterial for power generation. But through this one is basically nanogenerators technology use displacement current as a means to convert mechanical energy into electricity. So therefore, you may use nanomaterial, you don't have to use materials. It's a new physics field. It's up to the level of physics understanding how power generation is. So inside the circuit is displacement current, outside the circuit is the conduction current, capacitive conduction current. Both meet at the electrode. You see there's no medium here. So this displacement current goes from one side to the other one, forms a loop. That's what we observed experimentally. So therefore, Maxwell's displacement current give the birth of electromagnetic wave. That's what we use for wireless communication, everything today. Now, if you add a term here, this term is the fundamental of nanogenerators, TENG, piezoelectric nanogenerator, which is for energy and sensors. So furthermore, you can modify the Maxwell equations to include this one as a generic theory. But in reality, you can use this term to calculate all the power output you received in the future. You also can calculate the electromagnetic wave radiation due to TNG if you tap it at a higher frequency. So this is the basic way we look at how we can be contribute to fundamental. How can make an electrostatic charge give you power output is due to displacement current. Okay, so this is what try to make this clear. So now, if you got this, so how do you calibrate? Called figure of merits. If you work on many fields like the solar cell, thermoelectric, you have the way to do it. But for general TENG, you could not. So we build the models to study the figure of merits for TENG, and we try to maximize the voltage and the charge area so we can produce the figure of merits here. So you can look at original papers. We figure out what's the best way to calibrate to quantify the output of the TNG, so you can compare your device with mine. Yours is better by how much. So this figure merits derived that have some equation here. First one is materials figure merits. The second one is the structure figure merit. This one you can calculate based on the parameter used for manufacturing device. This one has to be measured experimentally. Let me show you the way. So this is the total figure of merits you can work on through here. For material figure merit, you think it's no. The answer was not. If you look at the textbook, find the triboelectricity, they give you this. There's no number. Until a couple years ago, until this year, we measure this quantitatively. What's the surface charge for different materials for a defined condition? So we measure this one. We have to standardize the equipment. We have to standardize the methodology. And we use the liquid metal to count all the materials. This is the 55 different materials, organic materials. We measure the surface charge density. For the first time, we give you the number to associate with this one. So this is another generic material genome. This is another gene for materials, which was not defined previously, but now we could. So this is the materials characterization. If you have new materials, use this technology to measure this one, you can know how much better is your materials compared to our materials. Now let's go to the application side. We talk a lot of fundamentals ones. Let's talk about a technology application. Why bother? TNG is a good way for converting mechanical energy into electricity. And this one is used a little graphene carbon as electrode, make a TNG to harvest energy from walking. For portable electronics, this uses silicon and silver nanowires as electrode to make a twistable, shape adaptable sensors as well as power generators. We also can harvest energy from a walking step. You can see the power output is not that small. It's significantly high for our some purposes here. Okay, and you can use for medical purposes. Use the breathing of a rat to harvest energy to power a pacemaker. And last year, we demonstrated the first commercial pacemaker driven by the TNG and successfully utilized in large animals. Show that we can use the energy harvest from the breathing of the animal to power implantable medical devices. I think this can have a great future in many different areas, implantable electronics, implantable medical devices here. You can use for drug delivery. This is with use TNG, without use TNG, the efficiency for drug delivery enhanced by a factor of 5. And you don't need to apply anything, just the physical motions, the voltage generated can drive the drug to infiltrate into skins. You can also use this one for fabric, because the material used fabric TNG can be fabric, can be anything you talk about that. You can make a fiber-based, textile-based machines, the power generator, as well as sensors here. So a lot of work on the fiber-based flexible electronics. How can you use flexible electronics to generate power itself so it can be powered? Battery is one way. Can you make a battery self-charging? You can use an actuator. You can TNG drive electrostatic motor. This motor can run at a high speed. Let me show you this one. This is a TNG. You can drive a motor here. You can slide it once. The voltage is high. drive this around 1,300 rounds per minute. So you can have an actuator one way or the other. Okay, we work a lot on power generation. We also work on a lot of the power management and also energy storage. Energy storage is different. Energy storage, we always utilize a DC input for power storage. But in environment, so much variables. So the input for charge the battery is not a fixed. So we have to do power management, put three things together: energy harvester, power management, power storage. We build a self-charging power unit, and this can give you a good summary of for the future mobile electronics. You should think the energy storage beyond the traditional value for energy storage. I think a lot of people just fix for DC input, but how about this pulse-based energy storage for that? So this is the power management circuit. You can design the circuits here. You can do that to give you a regulated output, So therefore, all this work are going in parallel. We have tried to do a variety to make sure this is useful. This is the new work done. We use the wind. You can drive the wind through this whistle blow. You can see the whistle blow here. And this is a small power, but if you put a few units together, you can drive a wireless transmitter and detect the environmental change, and you can send a signal at a Wi-Fi signal to a range of 50 meters or even to a few kilometers away. So this forms the network for environmental monitoring, for fire protection, for a lot of things you can do. You put environment, breeze wind is enough to drive this one for warning purposes. You can also utilize this one for example, floating the light tower in ocean, the floating water here, and also this one, you can see this is the floating water. You can drive this, okay? And you can utilize for this floating water. You can see this floating water, just water floating, definitely can drive, give you power for environmental monitoring. Lens sliding, if you have a tricky lens sliding, you can use it for early warning, for save lives. So therefore, a lot of this case, you need distributed sensors. Distributed energy plays an important part in that. Second part, cell power sensors. A sensor does not need the power, can detect things. We use a ping pong ball on the table as example. So the ball hit the up rim is available, put aside is not available. We use this one to design a table on the TNG. Here you can see that things can be, this is the available, and the hit TNG have a pulse. And if you hit the side, you get another TNG, not a two TNG. This is the side, a side one, this is the top one, give it another signal. So therefore, for smart spots, we recently wrote a review for advanced materials that on TNG for smart sports, basketball, volleyball, anything you think about, trick make a sensor system for the detection. Can you also for typing? We can use it for the identification purposes. Even you know the keyword you type in, but the way you type in is different. We can distinguish who typed this password in. That provided you have some kind of machine learning built in here. So this is the system we invented for that, for use typing behavior recognition. And this is for medical care. You can for sensors, for heart beating, as well as for blood pressure measurements. All these things is needed for here. So therefore, not only measure the heart beating, but for blood pressure measurements. And this one use recording, use paper-based TNG, can be a recording. You can record music. Let me show you. This is the original music. Okay? Original music. Then let me show you the playback. This is the playback. We did not add any digital filtering. Just 90% preserve the original music. This is the communication with robots. You can communicate with robots, and they can recognize who is talking. Therefore, can you ever think a paper-based TNG can be a micro, can be a voice recorder, self-powered, because it's give you power self. You don't have to be amplified there. So therefore, this show you a variety of possibilities. Let me just go quicker. Power from water droplet. we demonstrated the first wall droplet for power 2014. Use a wall droplet on the surface here. You can see this one. Okay. The power here. This was the one shows that charge transfer between liquid and solid, and use the single electron mode TNG to demonstrate that. Okay. We also recently show that this use can much more improved. As you can see that use just a few droplets, you have so many light flashing. It's truly amazing. There's no other way you can light so many flash in this way. Okay, so therefore little mechanical tricking, but charge on the liquid can make this happening. And this can be a good way for many things to study for that. So this one is you can use the YouTube, the change of the liquid shape here, and the power. So in that case, we do chemistry, we never realize there's charge things happening between the liquid and the solid that you can use output power, right? Can be output power. So I put this one, show you chemistry can utilize the contact-electrification between the liquid and the solid as a power generator. And let me just skip this one. I think my time goes very quickly. Large case blue energy, half the energy from ocean, half the energy from ocean. This is difficult, but we propose a way. We use this TNG to propose that way. You can put this water floating here. When the water floating, this ball flow back and forth, contact electrification, change the symmetry of the two electrons, have the electron flow back and forth, you can have a charge. So you put this one in the ocean, let's say in the ocean, slow motion, deep water, yeah, okay? Deep water. For this deep water, slow motion TNG is ideally for this case. The reason is because it has the very best response at low frequency. So we developed this a lot. We use soft ball. Compare hard ball, we can enhance the power output by a factor of 5. You can see just a simple change of materials, change output power by a factor of 5. A factor of 5. You can also utilize this one for the pendulum structure. You can one strike can make this pendulum oscillate for many cycles over about 100 seconds. You can have a efficiency energy harvesting. We found this one, we can get energy harvesting efficiency up to about 25%. 25%. You can use it in water, or you can use breeze wind. Breeze wind here. This breeze wind, harvest breeze wind energy is difficult because it's not enough to drive the traditional power turbine engine. Okay, so the key difference is TNG is different from classical technology in a way in physics. Materials utilized. EMG utilize coils and magnets. The power output is the frequency, square of frequency. TNG use organic materials, conventional materials. The power output is proportional frequency itself. So we have a low frequency. TNG has an unbeatable advantage. So what's low frequency? In our daily life, all low frequency. So compared to traditional technology, we have the complementary application. High frequency utilize the classic technology, low frequency use ours. Both can integrate together. So therefore we have our unique advantage in physics for low frequency energy harvesting. So put in the water, and you can do this one. You do solid dynamics, you can jump the ball. This one, let me see, you can have, all right, let me see. Right? This one, you can see all this jumping back and forth. So we have a large expectation in the future. We could utilize this water energy for large scope energy need. People may say, how much power you can generate? Well, we generate not much right now. But who knows? You can scale up. Look back to 1831, when Faraday first invented electromagnetic generator. How much power can generate? Very little. But scientists, engineers scaled it up. After more than 100 years later, huge power can be generated so that we can look for new material. So here is what's the opportunity for material scientists, chemists. I talk a lot about physics and design. what are the materials? From the theory, we say the output current is with the surface structure. What is the best surface structures? This need a material scientist to work on. For permittivity, what's the best composite material for this one? For the robustness, how can you make this last longer? How can you make the surface charge density goes higher? All these parameters are important here. Huge amount of research need to be done in this area. A lot of people work on a supercapacitor and a battery. There always you try new materials. But here for TNG, we have not even started. We need all kind of materials measurements to optimize the total output with this one. So I think it's a huge platform for material scientists and chemists to work on. Okay, let me just go quickly. Commercial opportunity, you have many things to do that. I'll go, but this one from the IDX the report, TNG by 2040 has billions of dollar market. Distributed energy have $300 billion market. So it's a big opportunity for many things. You can think about that, right? So let me just go this one. Oh, this is the first company we started 4 years ago, and this year we produced the air filter for anti virus, anti any application. But this year we have a lot of utilized for this the control of COVID-19, and so the sales is well, and also we make part of contribution to the society use the air filter for that too. So let me just go quickly that I only show that one flashing. Okay, so I'd like to conclude my talk here. I'd like to thanks for giving me this opportunity. Let me the summarize. We talk about the physics of contact-electrification, how the charge created. The second one, talk about how the electrostatic charge make a current. That goes to Maxwell's displacement current. We modify the Maxwell displacement current. We finally go here. Lastly, we show these 4 major area application for micro nano power source, solar power sensors here. So we even have a roadmap for this to develop in the future. So we hope to do. But let me show you a video. It was shot on January 1st, 2013. Was just about 1 year after we published the first paper on TNG. By today, there was 1,000 papers around the world published on TNG. 56 countries, 800 units, over 5,000 people work on TNG. Let me show you this video was shot on CNN on January 1st, 2013. 1 year after TNG was invented. And see my prediction that time. See what, let's see.
Professor Wang, the sound is not working.
You cannot hear the sound, right?
No.
Okay. So the name is the video I can hear, but you cannot hear on the other end. But let's go with I just ask the question with the audience. How about that? Hello?
Hello?
Yeah. Can you hear me?
Oh, yes.
Okay, let's. I'm finished my talk. I'd like to thank you for giving me this opportunity, and I wish KAIST a happy anniversary, happy birthday, and we'll be more than happy to do more collaboration with my career friends, scientists, and more information exchange. And I'll be more than happy to answer your question next.
Okay, thanks so much for your great talk. And here are the several questions. But due to the limited time, then I will select one question. Thank you for an excellent talk, Dr. Wang. With self-power, the TENG system, what level of voltage outputs are possible and what efficiency are currently looking at?
Very good question. The TNG has advantages, high voltage. Even you have a slow motion here, you see like this one, like this small device here, if I tap it with my finger, this is about 50 volts or so, 50 volts or so. And the voltage is high, the current is relatively low, but you can lower the voltage and raise the current, so meets the need for your application. The range can go a few volts, millivolts, to 1,000 volts, even 10,000 volts. So voltage is not a limit. The current is a limit. And current efficiency, let me give back to 2014. We published a paper in ACS Nano for review that we showed at that time the efficiency can reach about 50%. Sometime, depends on the design, you can reach 80-some%. Depends the frequency you look at that. So if you work on the ocean, we can get efficiency about 20-some% or so. So therefore, depends the case you applied, we can design for your purposes.
Thanks so much, the Professor Wang, for your precious time.